Good evening, everyone. My name is Lokesh Kumar Sharma. I am a student of SMVIT, currently in third year. And today we will be looking at a problem which is named B, Phoenix, and Beauty. It is a 1400 rated something problem. Let's forget about what the problem tags are. It is a B problem from some Division 2 contest. So the problem is something like it is about beautiful arrays. So consider beautiful array problems are like easy problems. Just make this in your mind, the mindset. It should be like this. So, what the problem says is Phoenix loves beautiful arrays, and an array is beautiful if all of its subarrays of length k have the same sum. That's it. This is the only problem. This is the complete gist of the problem. Rest of the things are just you know okay, theory kind of thing. A subarray of an array is any sequence of consecutive element. You know that Unix currently has an array. We will be given an array of length n, and we are supposed to insert some number of integers. We can also not insert anything into that array, and all of this insertion, not insertion, is just to make that array a beautiful array. What is a beautiful array? An array is beautiful if all of its subarrays of length k have equal sum. What do I mean by that? I'll show you once. So, suppose this is A1, this is A2, this is A3, this is A4, this is A5. So, let's say the k is here 2. The length of a subarray is k, 2. So, we have to make sure that every two element has equal sum, which means A1 plus A2 is equals to A2 plus A3 plus A3, is equals to A3 plus A4 is equals to A4 plus A5. We have to make sure of this. If the array is not in this condition, we have to insert some element so that the array becomes a beautiful array, which I have also explained what beautiful array is. So, and we are not supposed to the next line integers may be inserted anywhere. We can insert it on the right of the array, we can insert it on the left of the array, we can insert it in the middle of the elements, and we are not told to minimize the number of inserted arrays, sorry, elements. We can insert any number of integers into the array, be it 0, 1, 2, 3, anyone. The only condition is the integers which will be inserted in the array will be ranging from 1 to n. N and 1 both are inclusive, which means we can use 1 and n also for insertion. So the input is given some test cases of 50. First line of each test case contains two integer n and k, and which I have told you the initial length of the array, and is the k is the length of the subarray for which we have to make the sum throughout the array equal. So, and what we have to output, we have to, give the length of the new array which we have created by inserting some elements or integers, whatever you want to say. And we have to also print the array, the beautiful array. So yeah, that's it. So if we want to understand the problem more, let's look up the given test cases. Here are the given test cases. Okay, let's take one by one. This is the first example where n is equals to 4, k is equals to 2. This is our array. Can we say that every two element, this is, let's say, B1, B2, B3, B4. So we are supposed to make sure the array, in the array, every two element sum is equal. So according to that, B1 plus B2 should be equal to B2 plus B3 is equals to B3 plus B4. Let's say if it is equal or not. B1 plus B2 is 1 plus 2 equals to 2 plus 2. So it is kind of violating our beautiful array condition. So 1 plus 2. So what can we do? We can insert 1 in the middle. How? 1, 2, 1, 2, 1. And that's it. We have our beautiful array. What is the length? 5. And this is exactly what the given output is. So this is what the problem says. Now now one more example. Let's look at the last example. Okay, let's ignore this one. This is very easy, we can see it. 1 plus 2 plus 2 is equals to 2 plus 2 plus 1. So it's already a beautiful array, so we don't have to do anything. We will just return this array itself, which is like this. We can see this. Uh, for now, we'll ignore this one and look on the this one. So yeah, so we have to make every four numbers equal. So how can we make it? You can try this, of course you'll be trying and you must have tried this problem. Then you will be coming here to, look up the solution. So what must you have tried? A 4 plus 4, then 2, maybe then 4 plus 3, and another 4. So is this it? This sum is equals to 4 plus 3, 7. 7 plus 4, 11. 11 plus 2 is 13. Then again 3 plus 4, 7, 9, and 4, 13. Again 13. Then 4 plus 2, 6, 6 plus 4, 10, then 13. Then again 2 plus 6, 9, and 4, 13. So this is an accepted one. What do we have here? Yeah, you can, the given output is also correct, of course, which is given as 4, 3, 4, 2. This is what given to us. What the computer or the code forces has done is 4, 3, 4. I think 1, they have inserted 1 in there. Okay. Am I writing something wrong? Not exactly. Am I writing something? I am writing anything wrong. But what he has done is they have inserted 2 and 1, and then 4, 3, 2, 1, and again then 4, 3, 2, 1. That's it. This is what they have done. They have inserted 2, 1 two times. One here, and then 3 to 1, I think they have added here. I don't know, whatever it is. The main thing is every four element, every four element is summing up to equal thing. 4, 3, 7. 7 plus 2 is 9. 9 plus 1 is 10. 3, 2, 5, and 1, 4, 1, 5. So exactly. So this is what problem says. Now, let's look up to what our solution can be. Observation, or yeah. First thing first, what my argument is, we can see that what we have observed, that if we are given k is equals to 2, then every k plus 1, after every 2, for example k is equals to 2, so after every 2 elements, the pattern is repeating. What I mean to say by that is, suppose here is k is equals to is 2, and what are the initial two numbers, 1 2. So in the resultant array, this is the thing which is repeating, 1 2 1 2, 1 2, then 1 2. If we wanted to increase the size, we could have also, something like, this is the pattern in it, that this is the pattern. Oh, 1 2 1 2 1 2, and so on. This could have also been the output for our thing, because the computer or the code forces has said you don't need to minimize them, so we can add any elements as possible we want, but we'll keep it short, or we just want to understand the logic and all. And if let's come to the third example, let's make an observation for the impossible cases. Why it is given as -1 for this 3 2 1 2 3 example? Let's look at it. So, is it possible that we can create? We are given, we have to make every two element sum same, 1 2. According to our theory, our argument, what I just made observation, that if you want to make a beautiful array, we have to, follow a pattern like this, and we can't see 3 in it. Suppose even if we added 1 to 1 1 to 1 to 1, at last we'll have to add this, and this will break our logic, break our condition, because the last two elements doesn't sum up to 3, it sums up to 5. So what my argument is, if number of distinct integer is more than given k, then it's an impossible case. That's it. That is our one observation. Then the solution, how we'll be developing a solution. We can develop a solution just by making sure that every two element is repeated. That's that's it. That's the solution. Every k elements are repeated so that the periodic placing of elements take care of the required beautiful condition. That's it. Let's see. All we have to do, if we have taken care of the when the number of distinct element is more than k, then that's an impossible case. What if, let's see, one more edge cases. When, what happens when distinct are less than k? We have one case with ourselves, which is this. Let's copy this one and test it. So how many we want every fourth element together, then the repetition of it. But here the number of distinct numbers is 3 only, which is less than 4, of course. So what are we going to do in this case? We want A1, A2, A3, A4, A5, A6, A7, A8, A9, A10. Let's suppose this is an a random array, and k is given to us as 4. And so what we have to do? What does this mean exactly? Let's see. We have A1 plus A2 plus A3 plus A4 is equals to A2 plus A3 plus A4 plus A5 is equals to A3 plus A4 plus A5 plus A6. Last, take one another. A4 plus A5 plus A6 plus A7. That's it. Not more than that. It is more than enough to understand it. Let's cancel out the equal ones. So A2 will be cancelled if we look at these two conditions, at these two. A2, A3 and A4 will be cancelled out from these two equations. And we required is A1 is equals to A5. If we look at these two conditions, so A3, A4, A5 will get cancelled out, and only A2 and A6 will be left over. So we want A2 equal to A6. Then if we look at these two conditions, A3 is equals to A3 is equals to A7 will be left out. A3 is equals to A7, then A4 is equals to I would say 7, 8, following the pattern. So this is what we require. So we can see that if A1 is suppose 4, A1 is suppose 4, so we want the A5 element to be also 4. If A2 is 3, we want the A6 to be also 3. If A3 is 4, we want the A7 also as 4. And if A4 is 2, in this case, we want A8 to be also 2. But if we are going to, according to this condition, which I have just showed you, like this is how you should have a pattern or a periodic, yeah, pattern it is. But following this condition with these number, exactly these numbers, 4, 3, 4, 2, then 4, 3, then 4, 2. Is this working? For this case, it is working. Let's say I have an example, maybe 1, 2, and 3. What do you think? Will it work for this case also? Let's see. If k is equals to 3, let's see. So let's add here 1, 2, and 3. Is it working? Yes, it is working. Let's say we have uh, Is it working? We want 1, 2, 3. Yeah, 1, 2, 3. Then 1, 2, 3. Okay, fine. But what if there is a repetition of it? 1, 2, 3, 2. Will it work also then? 1, 2, 3, 2. Yeah. So we want three elements. So this is one. This is 1, 3. Then this is another 3, which is breaking our law. So it is not working exactly the way we want it. Then this is back to the same thing. Then again breaking our law. Then again to the rest thing. So this condition is not, valid for our case. But we can make one conclusion that to make this thing work, we can insert an element such that if it is repeated multiple times, our resultant array will be a subsequence of you know, the given array, which of course is also shown in the last example of it. What they have done is they have inserted elements in it. You know, yeah. How they have inserted elements in it? They have inserted 2 and 1, and then 3 and 1. What they have tried is they just made sure that this is 4, 3, 2, 1, then 3, 2, 1, 4, then 2, 1, 4, 3. It is they have made sure the pattern is there, and the only thing which they have to do is, just repeat it. So how we will make sure that, we have to make a general rule case which will work for every other case possible. So what I am thinking, what I have thought while solving this problem is the general case for every key elements are repeated so that the periodic placing of elements take care of the required element. We will just insert if the impossible case is done. Solution case. You know, yeah. So what will happen in this case? Of course, distinct numbers are less than k, then we will insert 1. That's it. How will it make work for our case? Suppose the given problem was 4, 3, 4, 2. So what are the distinct ones? 4, 3, and 2. Okay, let's insert 1 and then repeat 4, 3, 2, 1, 4, 3, 2, 1. We have our subsequence. Okay, let's say 1, 2, 3, 2. Let's see what are the distinct ones. 1, 2, and 3. Let's insert 1 and then repeat this thing. 1, 1, 2, 3, and 1. Is it making sense? Is it making sense? Yes, yes, it is making sense. Yes, definitely it is making sense. So yeah, this thing will work. So at last, if we don't need, suppose if there are four numbers, which we have seen already, that what if the distinct number is equal to k? Distinct equal to k. What will happen then? 1, 1, 2, 3, and 4. Simply repeat it. 1, 2, 3, 4. And see the pattern. See the periodic thing. 1, 2, 3, 4. And 1, 2, 3, 4. and then 1, 2, 3, 4. So yeah. So our solution pseudo code will be simply nothing more than take the input, take the input, count the distinct elements. If distinct more than k, see out, print -1, else if distinct more less than k, insert 1 until it is equal to k. Why am I saying this? Insert 1 until it is equal to 1. Sorry, k. Suppose we have an example. Let's create one. N is equals to 4, and then k is equals to 4. Let's see. So we'll have our example 1, 2, 2, and 3. Let's see. Let's make it 5 and add another 2. So distinct elements are 1, 2, and 3. That's it. Right? Let's add because it is short. Let's make this 5 also. So we are short by 2. 2 guys. So let's add 1, then 1. And then repeat this thing. 1, 2, 3, and 1. What is the sum now? Let's add another period of it. 1, 2, 3, and 1. So this is 1. This is one 4 element. This is one 5 element, sorry, because k is equals to 5. 3 ones are there and 2 and 3 is there. Then again 3 ones are there, 2 and 3 is there. Then again 3 ones are there and 2 and 3 are present. Then again 3 ones are there, 2 and 3 in present. So yeah, this will work. I just have proved you. And else if distinct equal to k, simply handle it normally. That's it. Now I hope this is clear. Sorry that I kind of you know was lost here somewhere, but then I got back. So yeah, let's look at the code now. So and yeah, this is the problem. Let's look at the code. Huh. We have taken input n, k, and the array. Then yeah, of course. Then we have created a vector of period where we will be taking the elements, and we have created this visited thing just to make sure that we count the you know that we are able to count the distinct element. I could have done using set also, but fine, it's okay. So what I have done is uh, I have traversed in the array and saw if it is not visited, make it visited, and also push it into the period vector. That's it. Simple. you know Only so what will happen if one is visited, pushed it into the period, and two is visited, pushed it into the period. Then two again came, but it's already visited, so it won't be pushed again into the period. Then one is also visited, then again it won't be pushed into the period. So we have our period as 1, 2. Okay. If the period size is equal greater than k, which I have told you, return -1 and return see out -1 and return. While period of size is less than k, because we have to make it equal to k, which I also explained it to you, we will push back 1 into the period array. Then the vector of answer. So what I have made sure that I have, we have to return the length of the new array which we'll be creating as beautiful array. I have taken a not random, but yeah, a general case where I'll be, printing every time the length of an array as n into k. So 4 twos are 8 for this example, you know, yeah, 4 twos are 8 for this example, and then I will repeat the pattern n times, which is 1, 2, 3, and 4. And the length is 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's it. What I have done here, I simply just, uh, yeah, printed the period n times. That's it. That's all for this problem. There is nothing more to it. I told you in the very beginning of this problem that beautiful array problems are easier problems. So you don't have to, get scared by such problem. Even after this problem is some 1400 something, but still it is. I will consider this problem as some 1200 something, but fine. At the first time when you look at such problem, they look difficult, but you, after a certain number of problems which you have solved of such pattern or types, you'll be able to recognize such problems, that how you can within time or within the contest time you can solve this problem with ease. So thank you for joining. Yeah, thank you.